So, ladies and gentlemen, welcome to this session about supporting open science and knowledge graph research infrastructure. We will have two participants here on the stage who give presentations, and we will also have two remote participations who will give the presentations from far away, so to say. My name is Jan Wiebelitz, I'm from the L3S, and I'm the moderator for today. Think about some questions that I can ask, that you will ask the presenters while they are presenting their sessions. So, about the session, scientific knowledge graphs provide a means for structured representation of information and thus facilitate open science by connecting scholarly artifacts. The question that we will try to solve today is how the Federation of Knowledge Graphs could provide various benefits serving the development of an integrated research infrastructure ecosystem. There's also some context in the upcoming work program of the European Commission, where scientific knowledge graphs are explicitly mentioned in context with the creation of open science and with DMPs. The presenters of today are Paolo Manghi from OpenAir, Sarala Wimmer-Laratne from DataSite, who replaced spontaneously more or less Gabriela Meyers, who could not attend this session. Then we have Jan Dvořák from Eurocris and Markus Stocker from the TIB in Hanover, who gives the presentations on research graphs, or graphs itself. And then Paolo will also give a report, more or less, about the activities of the RDA interest group on open science graphs for fair data. And then eventually we will have the discussion and panel and questions from the audience, which I hope are quite good. And now, just starting with the presentation from Paolo about open science, OpenAir research graph.
Okay, thank you. Thank you for inviting me. I think it's these kind of workshops and discussions are very timely. Open science graphs or knowledge graphs for scholarly communication and tracking with scholarly communication, making it useful and transparent and open to others to use are becoming a real trend. A lot of investments are necessary around them, and I think that the work that we are doing today here and in the RDA and in other initiatives, similar initiatives, is very important for the future of science. So just a few words on what we do in OpenAir. OpenAir is a non-profit company. We work mainly on open science, to put it short. So on the one hand, we care about alignment, global alignment on ideas, on work that we can do together to make open science a reality. On the other hand, we are also providing a set of services that is supposed to fill the gap, where the gap exists between the communities, the policymakers, all the stakeholders in science, and open science itself. We can identify three main, let's say, trends that we are trying to cover for. One is tracking. Tracking open science is a key and important action, which means the ability of collecting information around and everything that is an event about science, from the publishing of an object to the citation of an object to the usage of an object, and bringing together in one place where some observations, some reflections can be made. Then we have monitoring, which is typically built on top of that. So once you have this knowledge base that somehow represents what you have in mind, what you want to effectively track of science, and the features of science, you can monitor such features over time, across disciplines, interdisciplinary, and so on. And then, of course, you have the discovery that, again, based on this knowledge base that you're building, can be provided in many different ways, more or less advanced, but surely going beyond the simple full text search of a PDF, because we know that open science goes beyond that. Today, I'm focusing on what we're doing in terms of tracking open science. I will give you an iBird view of what we're doing in OpenAIRE to build this research graph. Of course, if you want to know more, you can contact me and we can share ideas, as we always do, with our colleagues in the domain. So what you see here is the information model, the data model, the way you want to call it, of the OpenAIRE graph. So the kind of main entities that we care about. As you can see, it's very CRIS and serif oriented in a way, because we are monitoring not only the production of science, but also, let's say, the administrative side, so the funding that is behind it. But we also care, and we care a lot about the interactions between the different products. So of course we have the authors. Of course, we have the organizations behind it, but we care about the kinds of products that we are producing, which we have classified so far in alignment with the IOSC in publications, data, software, and others, where others does everything that doesn't fit with the first three classes, and the interactions with them, so how they can be semantically be connected, okay? This is extremely important for tracking, again, for discovery, but also to somehow reconstruct what is being the science and the thinking behind one of these products. And of course, we have the funders, which play a key role here. So the idea is to build a graph that is open, means open access. Anybody can access it, is metadata. That we want to be open, CC0, as much as possible. That is complete. By complete, the rule of thumb is that anything that is a data source out there, so repository, archive, registry like ORCID or R3 data that is useful and trusted by scientists should be part of this graph. The duplicated, well, that's pretty obvious. We're collecting from different sources, potentially the same things, the same entities. So we need to put them together and keep track of where they're coming from anyway, to make them one object, however. Transparent, we need to know where the data comes from. So provenance for us is key, and is not only concerned with tracking which is the original data source, but also, for example, when we apply algorithms, because we apply many in the graph, tracking down what are the elements or the values or the relationships that we are producing thanks to a given algorithm. Participatory, because we exchange our data with many other initiatives, because we have about 30 team members that are very good and experts in many fields, but we cannot cover, of course, anything that is necessary in science to produce quality data. And so we exchange data. We want this graph to be participated. Decentralized, because we know that OpenAIRE is here today. It may not be, I hope not, tomorrow. So we want this data to go back into archives. So we have tools and mechanisms that allow the data that we are collected to be sent back to the original sources that were missing this data. For example, if we collect a record from you, you are an institutional repository about the publication, we can send you back the related funding, IDs to the funding, ORCID identifiers, open access versions, links to data, links to projects, anything that you're missing, and if you're interested. And trusted, because we want researchers to build on it, trusted services. We have many data sources. We count 97,000, from which we collect directly or indirectly. Directly, it's around 2,000. Then we have the aggregators and others from which we are collecting that are spread all over the stakeholders out there. So we have different types, from the publishers, from the individual journals, to the main data archives, to the registries, for example, Crossref, Data, ORCID, and so on, ROR. They are all part of our ecosystem. Software-oriented data sources like GitHub, we are fully integrated with Software Heritage. We collect bio-tools from Elixir and many others. And last but not the least, similar graphs like ours. So we started with Microsoft Academic, but we have open citations. We treat Unpaywall as a graph, and we, of course, have discussions with our colleagues out there in Europe. Now, the problems are the usual ones that you all know about and require completely different skills, and all together, combined, can deliver, hopefully, some accuracy and some quality and some homogeneity. So heterogeneity, key. We speak different languages. You can imagine what happens when metadata is concerned. So providing common guidelines is often not enough. Quality and accuracy is the same thing. So the quality of the metadata depends mainly on the data sources, but also on the practices of the different communities. So overcoming these issues is not easy. And completeness is, again, another issue. As I mentioned before, we want others that do a similar job to ours, but they do it in a different way with different skills to interact with us and exchange data. And this is why we came up with the idea of the Open Science Graphs working group. Now, the supply chain, I'll be very quick. We aggregate metadata, of course, from all these sources, but we also aggregate files because we apply mining to extract information from such files. We have around 14 million PDFs today, which we collect thanks to agreement with publishers or directly because they're open access from the individual sources. We include external big sources like DataCite, Crossref, and so on. We call them third-party datasets, so datasets in this case of metadata. We perform the inference and so on, and then we have different phases of the duplication, propagation of context, so many things that we can talk about forever, and in the end, we produce a graph. And we distribute this graph via APIs, via dumps, and via other protocols that we may find useful. These are roughly the numbers. We have 25 funders on board, counting around 3 million projects behind. For each of these, we run mining, so we check into the metadata of the PDFs that we have if we can find a match with a 99.8 approximation. We have more than 100,000 data sources now, which include journals. And overall, after the duplications, these are the numbers. Numbers are important, but are not everything. Quality is key, and our next direction, in fact, is this one. So we want to focus on be able to understand when a metadata is of a given quality because there was some effort behind it. Of course, we are not going to fill in the missing fields. We do in some cases because we can collect it from others who are doing the same job. But in some cases, it's simply impossible. And we need to help the user provide feedback to the researchers on understanding how to better publish the metadata. And this is going to be the next phase behind the graph. As you can see, we have 4.5 billion semantic links, which is a lot. And these are all links between these research products and all the other entities in the research ecosystem that I mentioned before. We have all sorts of PIDs. We are completely agnostic of the PIDs, schemas, and we keep everything about them. We track them as much as we can, and we have now fully integrated with the European Open Science Cloud. It's a big system, so I'm not going to comment on these numbers, but it is a big system. And we need clusters, quite expensive clusters to make it run because of the size of the data. And it's important to know that it's not a double-click installation, let's say. So it requires a lot of skills also in programming, from the programming perspective. It's not just about collecting some data and aggregating somehow. It's more of a sophisticated system. And again, I'm more than available to get into the details of this. Now, how do we include the data into the graph? We follow a path that is based on a clear onboarding mechanism. So if you're a data source, you need to comply to guidelines. You come to what we call OpenAir Provide. You register your data source. You validate your data source automatically against the guidelines. You get a feedback and a score on how good you're doing. So you can fix your metadata until you are, let's say, aligned with the expectation of the OpenAir/the EOSC today. And you can finally be part of the graph. We also have OpenAir users counts, which is a way to collect downloads and views from the different data sources that are participating to OpenAir. So we show into the graph, and we keep it to the graph, the aggregated information about usage data for publications, data, and software. So if we collect different downloads numbers about the same PID from different sources, we put them together, and we assign them to the individual object. And the brokering of metadata is what I mentioned before. So again, since we are collecting from you as a data source, if you're a provider, we can enrich your elements thanks to the participation of other data sources and thanks to our mining algorithms, and therefore we can send you back this information. We do this via a subscription notification mechanism, so you come up as a data source, you claim what you're interested in as events, and we send them back to you regularly, so to enrich your data. This is already embedded in some platforms like this space, not in the current release, but the software is ready and will be included in the next one. Usage. OpenAir is widely used now worldwide. We have, of course, institutions which are using our APIs and data, but we also have companies, Elsevier included, the Commission, IPSCO, if you know about it. Scopus is actually using our APIs. So whenever you click on your publications of Scopus, there's a request being sent to our APIs to collect the related data sets. Okay, so the related data sets that you see come from our systems. And we have many platforms that are collecting information straight from us, typically the European project full profile. How we provide access, there are open APIs. So when I say customers, in fact, these are happy customers because it's for free. At the moment, this is being covered for and sustained by the Commission funding until next June, and then other funds will come in and other business models will have to be applied. You can find everything at api.openair.eu. These are a list of key performance indicators you may pick in later on, but the idea is that also the dumps are being downloaded a lot. And by a lot, I mean a lot. Interestingly, there's one of them, which is the dump of funded products, which is the dump that contains the subset of the graph that has at least one funded products that is constantly being downloaded by services out there. So we count 45,000 now, but it could be 60,000 because probably there are systems behind, like company systems that are downloading this data to make on their own monitoring tools. These are the key performance indicators for Scholar Explorer, which is one of the most targeted API that we have. These are the resolution APIs to get back all the objects that are linked to a PID that you're providing. And again, this is used by Scopus, so goes high because of that, but there are many other services using it around, including repositories. This is the total and, let's say, a wrap-up scheme of the dumps that we have, which we regularly upload in Zenodo, so you may, of course, take advantage of that and do your own research or build your own services, and also give us your feedback and possibly suggestions. This was not supposed to be there. Okay, call for collaboration. As I mentioned before, we want to improve the quality, and so we need, of course, all the feedback that you can give us. This is extremely important for us because we need to improve what we do, but also because we cannot cover all possible skills out there. So we support access to the data, but we also offer you the possibility to enrich the data. So if you have nice ideas, you can collaborate with us and we include it. This has already happened, of course, given our possibilities and resources. And of course, as I mentioned before, it has a cost, the infrastructure has a cost, so we are also trying for the future to find ways to expose our services, probably via other projects, typically the funding services, the mining services, to others. So have open infrastructures like the ones that we are running with the data on it available to others to perform their experiments and also to help building this collection, which has to be perceived as a common good, and we should all care about it. That's it. So it's all. If you have questions, or Jan, maybe later, or okay. Thank you all.
Thank you. Now we will have the first remote participation by Sarala. She will present the DataCite PID graph. And my mic will be muted so that they can...
Hello, you can all hear me?
Yes.
Let me share my screen. I can't see there's a screen, so I will just assume that my slides...
No, not yet.
not yet.
Ah, but they're coming. Okay, excellent. Top right slideshow.
Slideshow.
A little bit to the right, yes.
Yeah. Okay. Let me get started. Okay, hi everyone. So I can't see anyone, so it's a bit strange. But anyway, I'm Sarala, the engineering director at DataSite. I'm actually stepping in for Gabby, who had a family emergency and had to leave early to Argentina in a rush. So apologies for all the last minute changes, and thanks for the organizers for really sorting out remote participation in such short notice. But I am really pleased that I actually got to attend. It was really good to hear Paolo's talk about open air. I will reach out to you later, Paolo. So today I'm going to give a brief introduction to the concept of the PID graph, persistent identifier graph, that DataSite is working on, which is somewhat similar to what Paolo is, OpenAir is doing, but we use different technologies. But conceptually, what we are trying to capture are the relationships and the PIDs. And I will also talk about the services that we are building around the PID graph so users can access this information. So essentially, the PID graph, the concept of PID graph that a dataset is working on, have places, people, things, and the connections between them. So for people, for the researchers, we mainly use ORCIDs, but there's ISNIs as well, and for research organizations, we use RORs, and for research outputs, it's mainly DOIs, and the DOIs can have links to other PIDs as well. So we believe PIDs and also the associated metadata, because those associated metadata are the ones that we use to create these relationships between different PIDs, are essential component of the implementation of FAIR principles. So, as Paolo already mentioned, as you all know, research is already a graph. So if you kind of focus on publication here, you can see it's linked to authors, other data sets, and references to software and other publications. And the authors have a relationship to institution, etc. So this is the kind of the concept that we are trying to capture in the PID graph. So all the PIDs are nodes in the graph, and the associated metadata really define the relationships between these nodes. And with this kind of bringing these links together, that means you can discover connections at least a couple of hops away or more, but that's a bit more expensive to do. So in general, we are mostly doing a couple of hops away. So one of the other most important things that for the researchers are the citations and references. So as OpenAir, we are also capturing this information. So it's important to note that citations and references are different. So citations are the incoming links, and the references are the outgoing links from a particular node. So we capture this is kind of the relationships that we use to capture citations and references, and there's more relationships that we use to capture other relationships. So the PID graph on the bubble graph shows kind of the content statistics that we have gathered. We did the numbers in August, and so it's slightly bigger right now. At the moment, right now it's slightly bigger, but So what you can see here is like data sets connected to software and people, organizations, publications, and funders, and all these nodes really connecting to other things as well. So this is what we have in our PID graph. So the PID graph, the graph, as in terms of content, we have all the DOIs from DataCite and a subset of publications from Crossref and all the organizations from ROAR, ORCIDs, all the ORCIDs from ORCID, and also software and funders. They are really part of DataCite DOIs there. So for the user, how do we get users to use this? The information that we have in PID graph is really DataCite Commons. So that's kind of the user interface that we have developed so that the users can query our PID graph. So let me actually go to the DataCite Commons. So the service is called DataCite Commons. So I thought I'll just use the live website rather than going through the slides here. So you can search for works, which is DOIs, people, that's ORCIDs, organizations, ROAs, and here, as you can see, we have an outlier repositories. So at the moment, there's no PID for repositories, but we wanted to kind of capture this information. So there are discussions discussions in different grants about PIDs for repositories. But in this case, we're actually using internal identifiers to group. And we have all the repositories from DataCite members and also read3 data. So you can search for those here. So you can select a tab and type in what you want to type in to search. So here I'm using the same example on the slide here. So just looking for this specific data set, and you will get a results set, and you have the filters to filter out the results set. And then you can click on this individual information, individual line items, which will take you to the DOI in this case, because we are on works, and it shows you the aggregation of information. So here really at the top is just the summary, and if you have the authors linked to ORCIDs, then you will get the links here as well. So at the moment for this data set, it's only the link to organizations, so it's triad here. And you can see that there's some description and citations, the number of views and downloads we've gathered, and the creators. And you can also download this information. If you're logged in and you're an author, you can claim this DOI as well, and citation information. And here it's like more giving the views and downloads in a more visual format here. And at the bottom, we show the references and the citation list. And then if you have a long list of references and citations, you can really use this filter to filter out that result set. So this is really DataCite Commons. It will be really good to sort of hear feedback from you if you use it. Let me go back to the slides and find where I am. So going forward, what we are really doing is trying to expand the content of the PID graph, and also improve the services around the the PID graph. So really focusing on the aggregation of information in DataCite Commons. So we have several grants to really work on that, and also expanding to get more links from others, and also the PIDs from other resources, and also really providing a better way to harvest this information. So right now it's not so, you have to use the APIs. So we are really trying, as part of one of the EOS projects, we will try and build the sort of data dumps, and how can we make it easy for people to use our data in their own systems. So more sort of supporting integration. So yeah, please go and visit DataCite Commons and give us feedback, because next year we have several grants working on improving DataCite Commons and the content. Yes, thank you so much. So that is end of my slide.
Thank you, Rada. And now we are back here in the room with another presentation live on stage, so to say. Ivan Dvořák will present the glasses. The serif graph. This is probably wrong here. Slideshow. And here you go. Thank you very much.
Thank you. Hello, everyone. Welcome to Prague. I hope you are enjoying it so far. I will talk in the context of knowledge graphs about SERIF, the Common European Research Information Format. And that's a thing that is seen in the context of current research information systems. So these are the beasts that somehow help organizations to collect, manage, document, report on, and disseminate information on research activities that are done at an institution, or with funding from a funder, or by institutions in a country or region, then you have some sort of governmental crisis, or using a research infrastructure, which I think is quite important here at EOSC. So what information would you find in CRISIS? Basically these kinds of informations, the research outputs, but also the information on projects, on the funding, on the persons doing the research, on the organizations, and once again, research infrastructures. But it's not this easy. There's a lot of richness under each of these boxes here. So it's basically the researchers, but also doctoral students, visiting staff, librarians, administrators, the management of the institutions. It's under organizations, you first of all need to map your internal organizational structure, then you can track collaborating organizations, facility operators, funders, industry partners, different consortia, networks, societies, publishers, patent offices. And similar in the context of research projects and research outputs, and you can imagine this is going on. And with research infrastructures, you also track the facilities, the large pieces of research infrastructure, but also the equipment, and what is most important, I would say, the services that are being offered or consumed. So SERIF is aiming to be a comprehensive data model for research information. So the entities are those that we have already seen here. The projects, organizations, persons, funding, different kinds of research outputs. but also events, research facilities, equipment, services, skills, prizes, and also indicators, so quantitative and qualitative statements about things. There are 25 of these in total, and they have the basic attributes. We know we are living in a multilingual world, so the free text ones allow for multilingual variants, and of course all the different kinds of external identifiers that are out there. And the most thrilling part, the relationships between these objects. So in the model they bear formalized semantics for the types of the relationships. They are generally many-to-many, and they can have information about the time frame, so about the optional start date and end date. So this can be important if you want to track changes. Wow, this is a little bit disturbed, but nonetheless, this is what the model looks like. Currently, there's an example of a data set originating from a project. The project has a work package as a part, and the project has a person in the role of a principal investigator. Then we have a second person who is the work package leader. But what then happens is that with time there is the date when the project starts. But then the second person can replace the first person in the role of the principal investigator. Which does not mean that we have to erase the information that person one was the project leader, was the principal investigator. We just set an end date on that and say that, okay, that was true until this date, and starting from this very date, the second person becomes the principal investigator. If you want to do any kind of analytics, this is basically vital to keep the history. And then the project ends. So that's an example of usage of these start dates and end dates that can allow you to sort of work with the data in novel ways. So this is all a mesh of information, of objects that are connected through links. This is an example. We are using serif as the basis for the ingestion format for OpenAIRE, namely for the OpenAIRE guidelines for CRIS managers. And this is, as an illustration, this is a set of examples that we produced to illustrate what we are talking about. So the different colors here, those are the different types of entities that you would meet in serif, and you see how interconnected they are. So basically this looks like a normal graph with edges and nodes. And the nodes, those are the typical suspects, such as projects, organizations, persons. You've seen the idea already in the previous presentations. But we are going a little bit further here. We are undertaking a refactoring of serif because we have observed quite a couple of things that are not quite right with this picture. One of them is that the binary links, they are not always sufficient. So where you most likely meet this is with representing affiliations. Contributors to research outputs often come with an affiliation to their department at some particular institution. Also, participation can happen in different capacities. So you can have a capacity of a researcher in one institution than perhaps of a person working in a scientific society and having a position in a journal board, editorial board, and so these are the different types of context that are simply important if you talk about a person who has done something or is about to do something, or organization unit. And also, if you have different quantitative statements, they often relate to more things than just two. So it's also something that you need to bear in mind. To illustrate the affiliation idea, let me give you here a scale between a person and an org unit being connected to something. In this case, being a member in some organization. So on one end of the spectrum, we have the person. The person is the member. On the other hand, we have the organization unit, that is the member. Now, with the person, there is the question, where does that person actually come from? Why are they there? Person can be a member, but there is additional information where they come from, because the person is affiliated to some organization unit, meaning an institution and also a department within an institution. Similar, if you mention just the organization unit that is member of some other organization, then the clear question here is, who represents that org unit? Who should we talk to? And then you have the other options, that the org unit is the member, but it's represented by a person. And sometimes this can even be connected to a position. So the director of a computing center represents the computing center in some other organization, for instance. So we guess this is pretty important to bear in mind, and the affiliations, you can't distinguish them by time, they just intertwine. So we need to keep the information on a case-by-case basis. It can be different on different publications, on different presentations, on different projects. Why are we talking about current research information systems? So there is certainly some planning of research that is going on. There will be funding call descriptions, and then the funding applications that follow these funding calls. They should be also represented in serif, that's what we think. And also research infrastructures should have structured descriptions, which should be processable by machines. And then the research infrastructures can be searched by researchers, and these can formulate the usage proposals. And then also the evaluation outcomes of these applications or proposals. They simply deserve to be represented as structured information. Then we have ongoing research. And then reporting is the key aspect, because the quizzes, they just save so much time of the researchers on reporting, because they can shield them off from all the reporting requirements that are coming. And last but not least, it's the past research that is of current interest, which is seen as contents of the quizzes. So we basically think that we need to expand a little bit more, and it also applies to the research graph ideas, that also the offerings of the research infrastructures should be somehow represented, made part of the graph, and possibly also the usage of research infrastructures would deserve to link to these offerings, to show not just the data sets, but also the research infrastructures that were used in some research. And that will be probably all from me today. If you wish to know more, we are holding different events at Eurocris. So this is the closest one at the end of the month. We will meet in Nijmegen in the Netherlands. So thank you.
Thanks. So I guess you have all burning questions, but we have another remote presentation by Markus Stocker about the Open Research Knowledge Graph. And yeah.
Yes. Hello, can you hear me?
Yes.
Super. And I guess you can also see my slides. So, welcome everybody, and I will talk a little bit about fair scientific information. We had heard a lot about research information, and maybe I can make a pitch. There's a difference between research information and scientific information, and basically what I'm trying to do is go a little bit more fine granular from links between entities like data sets, articles, and organizations, to dive into the content of the articles, so the scientific information. And I will do that in particular with the Open Research Knowledge Graph. I'm Markus Stocker, and I'm with TIV in Hanover, Germany. So let's start with the highlighting that scientific information is data. I guess that's not controversial. So as you can see in the plot here, these are data points, so these are visualizations of data. And this data is not fair, so meaning certainly machines have a hard time to reuse the scientific information in articles. They can support keyword-based search, but beyond that, it's really hard for them to make sensible use of this information. Essentially, when we do a literature review or research for literature, for scientific information in the literature, what we do find and access are documents which we then need to read. Let's look at this document a little bit more closely. So at the first paragraph, there is a sentence here that says IRE binding activity was significantly reduced in failing hearts, and there is a pointer to the figure 1b. I'm highlighting this on the slide here. So there in the figure 1b, there is a plot that I already mentioned. I'm making it a bit bigger here. And as you can imagine, this data is actually CSV data, just a visualization of it in the paper. And what you can see here is that it's very hard for even humans to tell whether these are 5, 6, or 10 data points or the actual values. And the same is true for the p-value. I'm highlighting here as well. This is generally an approximation, 0.001, and not the actual number, which could be several orders of magnitude lower than that. So what a machine would show or should consume is something like this. So we have here a student's t-test. Of course, there are vocabularies for this. The ontology for biomedical investigation is a class for students' t-tests, and this student t-test has a dependent variable that's iron responsive element binding. I'm looking also at the gene ontology here for a term to make this machine interoperable and fair. Has a specified input, this student t-test. That's a CSV file that is plotted in the paper, but here I would like to have a link to the CSV data, or actually an ingested version of it into a database, so that machines can even access this more flexibly, query it, and so on. And of course, the t-test has a p-value, that's the specified output. And also here we have again terms that we can reuse from the ontology for biomedical investigations. And the scalar value specification of this p-value is the number. And as you can see here, I don't have 001, but the actual not p-value. And that's important for things like systematic reviews, because of course it matters whether you're reusing a value 001 or 01 versus the actual value, which again might be to the power of -8. So Barr and Mons pointed out a long time ago in 2005 that essentially scientific writing can be called information burying. So that's what we do here. The information that we produce, which often during the life cycle is in structured form or more structured form than when it's presented in articles, is essentially buried into text. And then we mine it again. So we extract it in very expensive and inaccurate manner, extracting it again from the text. Teresa Atwood then a few years later also pointed out that we have essentially failed to organize information in rigorous ways, so that finding what we want and understanding what's already known become increasingly costly experience. Think about any systematic review team today needs to read hundreds or potentially thousands of papers, extract manually content from articles in order to create databases that then power a new analysis. And that's extremely wasteful in time, but also inaccurate, because often, as I pointed out before, you can't actually extract the actual values from these figures. Plus, as Julian Higgins and colleagues point out in a Cochrane training handbook, despite the recent developments in machine learning, data extraction is still largely a manual process. So most of the effort that goes into extraction from articles is an expensive manual process. So that's a problem and why it matters. Lots of communities have done a lot about this issue. So I would like to just highlight a few of these communities that have extracted data from articles for their own purpose, usually for a particular research area or domain. And they built, not just published the data, but also built on top of it services for visualization and further analysis. So one example or two examples on biodiversity. One is High Knowledge that has extracted information in invasion biology about the support that various hypotheses in invasion biology have in the literature, and then created these visualizations, these networks that show the relationship between hypotheses and also their support or questioning in the literature. Another example is Platzi, which is also in the biodiversity, and I think it's a very well-known service with, again, information extracted from literature extracted in databases, so that this information is more reusable. In social science, there is the Cooperation Data Bank. As you can see here as well, data extracted from about 2,000 papers, organized in databases, in this case even a graph, so a triple store as a backend, in order to power then tools, analytics, including geographic analytics. The air quality data collection at Forschungszentrum Jülich is another example. Data extracted from about 150 publications, around 1,000 measurements here that, again, they have created a database and on top some basic analytics so that you can explore this data. Papers with code is not a good example in machine learning. With data, in particular metrics for the performance of models that, for instance, detect objects in images. There are a number of benchmarks for this task, and people develop models. And by simply extracting the performance, so precision recall and F1 scores, or the metrics that are shared in this community, you can easily compare the performance of models and also plot the trend of models in the community over time. So you can see how well a community improves. And finally, also MetaLab is yet another example in cognitive development research. So you can see that there are many examples of communities that have created such databases, and of course any systematic review team extracts and builds databases with scientific information. Often these data sets are not published, and even less often the community builds some services on top of it, but there are indeed quite a few examples where this is the case. And finally, I would like to highlight also the Open Research Knowledge Graph, which has similar goals, but in contrast to the previous examples, tries to address this problem a little bit more in a generic sense. So the examples that you showed before were strictly in a community. There were also services that were tailored with visualizations that make sense for the particular kind of information. And Open Research Knowledge Graph tries to address this issue a little bit more broadly, and also to try to catalyze a transition or a transition from purely classical publication, scholarly communication, text-based, to more fair scientific information. So I think the benefits are obvious. Once you have a database with information extracted from the literature, you can also easily compare this information, for instance. So think about this like Amazon product information comparison. So you have here in the columns different research contributions of papers. In this case, we are looking at SARS-CoV-2 basic reproduction number estimates. And then in the rows, you have a number of extracted properties about this research contribution, in particular the value, the estimate itself for the SARS-CoV-2 basic reproduction number, which in this case is 3.1 in the first paper, 3.6, and so on. So you can more easily compare the value, how the value behaves across the literature, and also, of course, reuse this data set, which is now simply an Excel sheet in a way, so that you can filter. For instance, you can do regional studies for the difference in Europe versus other areas, or so and so on. You can also create nice visualizations of more complicated data that includes maybe even processed data from various comparisons. In this case, you have the case fatality rate and withdrawal mean, plus the average basic reproduction number and withdrawal mean. So together you can essentially plot SARS-CoV-2 for its deadliness and contagiousness in relation to a number of other infectious diseases. So here multiple data sets come together, and you can relatively easily now create this kind of products. And this is also made possible by tight integration of ORKG with computational environments. As you can see here, we can simply read the data of a comparison, which again is essentially an Excel sheet or a data set. By giving here a comparison ID, you can simply read this into a data frame in things like Jupyter notebooks or R, and then you can manipulate this data in these computational environments. Other benefits here is the integration with existing research, scholarly communication infrastructure. We have just heard from Salara, who introduced also DataCite Commons. You can discover these ORKG comparisons also in DataCite Commons, because we allow for persistent identification of these assets and using DataCite UIs. So you can discover these resources also in the PID graph. We do link also comparisons with the underlying papers that are essentially cited or from which information is extracted. So this is just a screenshot that shows the related articles that are used in these comparisons. We can do also the other way around, basically given a paper, here transmission potential of COVID-19 in Iran. This is a cross-ref identified artifact, and since it's cited by our comparison, you can then also discover the comparison. So the question is, why is most scientific information still buried in documents if the benefits are this obvious? And one reason, and that's perhaps the hardest reason, is indeed because I think producing fair information, fair scientific information is really hard. So what do we do about this? And here at in the ORKG initiative, we have essentially three approaches that we are pursuing, three modalities to ensure that more of the information produced is fair and reusable by machines. So one is crowdsourcing. So this is what we call a post-publication manual approach. So the article is written, the article can be read, and the crowd, either the authors or readers, can extract manually information from the paper and ingest it into ORKG. So we have an interface for this, and here I'm showing the case for the basic reproduction number again. So basically a statement browser, we call it. You can simply create new properties and attach values to these properties, and these can be, again, complex information objects with further structures. So for instance, here for the basic reproduction number is 3.1, but that's actually a resource that has a confidence interval attached to it. Also, location is Lombardy, Italy, you see it, but it's actually a resource linked to geonames so that we can also ensure the interoperability of this data. Same for time period, has a beginning and end, so it's an interval with a beginning and an end date. So this route or modality for creating this content has, of course, the problem of scalability. So manually, it doesn't really scale very well, but has the advantage of accuracy. So experts generally tend to make less errors in this task than machines. So the second route is, as you can guess, also an automated route. So that will be post-publication as well, and it's based on NLP. So the idea of training models that are able to extract information from title, abstract, or full text if available. And as you can see, what we do here is next to the statement browser, there are some suggestions now that the machine provides for information that might be relevant to extract. So there could be, for instance, the research problem or some resource that is then identified like sensor data that you can then further describe. Of course, that's very high granular. The machine doesn't get into things like the data that I showed in the plot. So that's not possible to extract in any reliable manner. So the users would have to somehow provide that data then also via crowdsourcing. So a third approach that we are investigating a little bit further is by what I call the pre-publication and fair at birth. So essentially, going back to Barr and Mons, avoiding that this information is buried into text, ensuring that it's produced fair, machine-readable, upfront, pre-publication. So essentially by building technologies into the data analysis phase where you anyway compute these t-tests and linear mixed models and so on. So here is an example that I'm showing you a little bit of snippet of code just to show you that essentially we integrate here the production of fair scientific information into the data analysis phase. We have here some data frames as output that are then passed directly into the steps that ensure the machine readable information is produced. And what happens then is that these files are submitted, so that's the idea, that these files are submitted to some publisher together with the article, here exemplary Copernicus publication, and then the publisher would ensure that there is a DOI link between the article and the supplementary materials. And now you can guess what happens when you have set this into infrastructure. Given a DOI, we simply can harvest this content. And this is what happens here. So given the DOI of the article, we can simply harvest the descriptions of the research contributions that are produced during the analysis and published through the review process, through the publication process. And here is an example for the linear mixed models computed in the previous data analysis step with the input data set here pointed to the Zenodo data set, which is a relatively large data set, and it's not directly mentioned in the article, so we don't consider that scientific information. The model, a description of the model, in this case it's a linear mixed model, and then the output data set, which is actually a table in the article itself. So we ingest this data now through the data frame that I showed in the previous slide, directly the whole table essentially, and this is now a harvested data, but also again readable into Jupyter Notebooks, so that, for instance, you can power systematic reviews using this data. So thank you very much for listening and your attention.
Thank you, Markus. Okay, stay tuned. We have just the last presentation. We have now seen a presentation about graphs from kind of infrastructures, but there are, of course, tons of graphs from domain-specific organizations, institutions, projects, whatever. And now Paolo will give a final presentation for the session today about the RDA interest group on graphs.
Thank you, Ian. So I'll make it fast as much as I can, so we can share some of the time and spend some of the time discussing and asking questions. So it's clear that graphs are useful. They have a mission. So the open science movement is pushing a lot for this, because we want to have free data on top of which we can reflect, make our ideas and thinking possible. Okay, and today, unfortunately, as we know, the known enterprises actually own most of the content, and this is a barrier for us. So we are not able to assess, we are not able to track as much as we want unless we pay. So it's clear how these open science graphs knowledge initiatives are flourishing, and why, and what is the usefulness behind. So this is pushed by the fact that we are publishing research objects that go beyond the publication, but also to the fact that we would like to go in the direction of tracking the evolution of science. So the investigations that we are performing, carrying out, bring as output many other entities that are as relevant as the publication. And so we are all here thinking of how to make this possible in terms of practices, in terms of semantics behind, in terms of modeling, and so on. So what Markus has just described is a clear need, right? And it's one of the pushes that is taking us here today. So many have started, since this information is available out there, is actually available, collecting it and making sense out of it. Typically making it homogeneous, fighting against heterogeneity, but making it clean and for others to be used. Okay, so here, what I'm mentioning here are many of the initiatives out there that are working in this direction, more or less open, more or less made for business, more or less sustainable and no profit, but still, they're all going in the same direction. So they're trying to collect information, metadata, typically, enriching it as much as possible and making it available to others for thinking. So each of these initiatives has its own teams, its own skills, its own ideas and missions. De facto, they build graphs, okay? And by graphs, of course, what I'm implicitly meaning here is not that there's an RDF implementation behind. So the graph, the term graph should not be interpreted as a technical let's say, concept, but more of an abstract content. So each of these collections, in fact, exposes behind a number of entities connected by relationships, okay, connected by meaningful links. Scopus, for example, is a graph because it contains publications, it contains authors, it contains organizations. DataSite defines a graph, okay? So all these are able to expose such networks. So if we take any of this, you will find out that they are trying their best to interact with others of the same kind, okay? Because they know that some information is exposed by others that they cannot by themselves find, and therefore they interact and they try to find ways. Unfortunately, this is a rather expensive job. I'm not sure you've tried, for example, to download the OpenAir Graph or to download Microsoft Academics, but it's blood sharing, right? So it's not easy to understand what these graphs are exposing as an entity. If we are talking about the same thing, are we talking about a publication with the same interpretation? Is a data set the same thing? Are these relationships interpreted in the same way? So there's a strong need to sit down and discuss. So we started 4 years ago, I don't even remember, Marcus, maybe you do, discussing these things in a paper, these aspects, with DataSite, in this case OpenAir, a resource graph from Australia, and we started thinking about this working group. So the idea, again, is to capitalize on synergies. So since you know your business, I know my business, we have our ideas, customers, and vision, we are building graphs, let's find ways to speak the same language and to exchange data in a way that is as easy as possible, as easy as possible for others, and that facilitates in general the exchange of information across these different graphs in a way they can interpret not only what it is about, the data that I'm collecting, but also where it comes from, how trusted it is, if it's been inferred, if it's been collected from data sources that are the same as mine, and so on. So for this, we needed an information model, so to sit down and again discuss with the critical stakeholders here, so those who are playing a role. Sarif, for example, certainly has to sit at this table, but also those graph developers, also the publishers, and discuss how to find a common model. And then, of course, the technology behind, so the formats that we're going to use, if we can decide, and protocols, and so on. Scolix was a good experience already run by RDA in the past years, which translated from an information model into several implementations now used worldwide. So we wanted to follow the same path and experience. So we had a quite strong group of people, people that you know, people who made the history of scholarly communication in many ways, long before we were all born. Crossref, DataSite, Sarif, DataSite, Open Citations, for decades they've been around. They all share the same need and would like to participate. So they sat down there and started this discussion. Now, you won't remember the link and the URL that I put there, but if you search for Open Science Graphs RDA, you will find the link to the working group. So the basic idea is very simple, is we should all be able to interpret and view an open science graph according to a common lens, let's say, to a common information model with very specific meaning that we all share. This means that every graph should, of course, map its own local interpretation into this model. And of course, to this model, we should have a corresponding metadata format through which we can exchange the information. Could be bulk, could be through APIs if we find also common protocols. So if we build something on top of that. We are starting incrementally, so we start from metadata formats, but more may come. Another interesting aspect is the notion of profile. So a profile is basically metadata describing a graph. And here we can really play a lot and go well beyond what's available today. The idea is to have a catalog through which I can select the graphs that I need based on the data sources they aggregate, based on the tools and the methods, because these will be linked to papers that they're using to build the graphs, based on many factors that we believe are important to characterize a graph of this kind. Okay, so these are mainly oriented to researchers, but also to service providers in this case. So we had 4 task forces that are today operational. The first one, we should conclude its operation this month, is Task Force 1, so the Open Science Graph Core Information Model. Again, the approach is incremental. So we wanted to start from a number of entities that we were all interested in as graphs, as initiatives, and start from those that were, let's say, most populated by all of us, from which we had a real interest. And for each of them, then we wanted to find the properties and the relationships which we believe to be important. In the second task force, which will start November, ending next year, January, we wanted to define the commons, so the metadata format, actually the metadata exchange, okay? Because defining the model is not enough, and or adopting a model. Hopefully we'll find something out there that has already everything as a package, but then we need to establish how we are going to expose the data. XML, JSON, JSON LD, whatever, but we need to decide and sit down. Even multiple ways of doing this will be possible. And of course we need the crosswalks from all our internal models to those. The third has to do with access protocols. Here we would like to think of which are the easiest way and most immediate solutions that we can find to make this data shareable. Of course, providing a dump, FTP, great. Zenodo dumps are amazing, but maybe there's something more that we can do from GraphQL, special RESTful APIs, even SparkQL. And then finally, the profiles, which is, let's say, a nice cherry on the cake, which can come at the end, could be really interesting, but it's something that we like to think. After these 4 task forces will be concluded, we'll have another round. And for example, we need to approach the problem of provenance, the problem of tracking the quality of the individual records that we're going to share, okay? Some of these graphs do, others don't. Describing how a record has been produced, thanks to data collection, thanks to specific data harmonization rules, thanks to specific mining algorithm, is extremely important to be able to reuse the data in a way that is meaningful. I cannot just trust a piece of information that comes into my own database. So at the moment, basically, we have identified a long list of entities that all the graphs that I mentioned before somehow touch upon, okay? And we have then built a matrix, and we try to specify which graph implements or includes which entity. So a sort of selection based on popularity. We started from those, the ones top right, which as you can see, are the most common, effectively. So the products are publication, data, and software. They all have them, they all want them, and they want to deal with them. Then authors, organizations, journals, topics, and projects. There are many that are left out. For example, services, one of them, which we are not touching upon today. This will happen in the second round, but that's the idea. So join us, please, because the more we are and the more we agree on things, the more we want to experiment the outcome, the more we'll be successful. And thanks.
So, thank you. We have Jan and Paolo. Would you just sit on the panel chairs and then I grab the other mic and run around and see if we have some questions. Here's a mic. Who has a question? Excellent. So starting the discussion is the most hardest thing. Thank you.
Hello. Florina Piroy from TU Thank you very much for your presentations. I have a really long list of questions. I hope we grab a coffee together afterwards. Main one, you are encoding a lot of information in these graphs, and I have the feeling that we are now becoming captured in this yet another numbering system. So if my data set is in the graph and I'm visible and so on, and you are doing lots of automated processing, and I know alone PDF processing is a highly error-prone pipeline and process. Do you have any assessment of how much is wrong in those graphs and how much wrong data you ingest and you present? This is one question. Then the second one related to your last presentation, which really highly interesting. why aren't you looking at, so I got reminded very much to these top-level ontologies which other domains are working with. And they are trying a lot to do exactly what you're doing. You have different types of encoding this information, graphs, ontologies, whatever, and then you try to match them somehow. And they have something which is called a top-level ontology, which has just some basic information about something, and then they map them down to the others in more specific ways so that you have a mapping between the various graphs.
You want to start with the first one?
While the other two here discuss who will answer the question, Markus and Sarala, would you like to open your video so that we can see you, please? Excellent. So Paolo, Jan, Sarala, Markus.
I can answer both, but of course I think all of my colleagues here have their own ideas. So the first one, I'll be blunt. So there's the main issue that we have today in building this graph is the authoritativeness of the information that we collect. So in some communities well behave. We know that what we collect is correct. In many cases, we don't know what we're collecting. So we just trust what is there. But the lack of practices is the main issue. So validating them, trying to understand if what we collect is correct or not, is something that can only be performed by humans in a second stage. And for some of the things that we do, we of course have that. I mentioned we have 99.8% approximation when we when we infer funding. And that's because actually a human being, for every single record that we are mining for, actually verifies that this is really the case. But you'll be surprised to know, just to tell you how the world mad is that when we give this information to the European Commission, so the Sigma portal, actually, if you're an officer, if you're the coordinator of a project and you want to report your publication, you go to the Sigma portal and you find there the suggestions from OpenAIRE. Okay, so you find the papers, the data that are likely be linked to your project. You may be surprised to know that many of these are rejected. And when we go and check in the acknowledgement, there is the project, right? So validation is quite hard to do. It's quite hard to do, and probably should be done by a team of people rather than one person that is somehow elected, and of course manually verified. But the process is missing. The whole process is missing. So we are all trying to do our best to make sure that it is correct. I wouldn't bet my hand, though, never.
And this starts at institutions, because institutions with their crisis, they want to collect the information on what's going on in the institution, research-wise. And sometimes we find that the information quality is good. Sometimes we find that it's just good enough. So for some purpose that is at hand at the moment of collection, and then the information is just left there and used out of the context, and sometimes that doesn't work. At the institutional level, that's extremely difficult to assess, the percentage. Yeah.
Further questions? Excellent. Yes, good. First.
Hi, hello. Thank you for this very interesting presentations. My name is Heinrich Wiedmann from the German Climate Computing Center in Hamburg. Some question to Sarella and Paolo, but as well maybe to the others. So about all this kind of graph, so the PIT graph and the research discovery graph. So is the intention? So I know that is to bring this together. So the research discovery graph will use the data and the information from the PIT graph, and as well, it's maybe then the next question, how you bring together the open knowledge graphs together with research data graphs. So it's a big question, how to bring this all together. And so, because finally, I mean, the vision is that you have finally a single point of access, and then you can all the end users can discover and find all the information of all these kind of graphs. Yeah.
Sarala, you want to give it a go?
Yep, sure. Good question there. So at the moment, we don't, we harvest a little bit from Crossref, but what we've, so we tried to build a graph with all the Crossref nodes, but the problem is it's very expensive, as Paolo said. So now we are kind of rethinking our kind of point of view, where we have all our data sets that our members create. So they are really coming from the members. So the metadata, we are really still trying to encourage to have more metadata as well. And then we will have the links to the relevant information. And at the moment, I think Paolo is OpenAir is already harvesting data site data. I'm not quite sure whether we will be in terms of integration, whether we will be importing all this other information, because it's really a costly exercise. So the best way, I think, for sort of a more of a cost-effective way is really provide this information in a more efficient way to the users to get this information to do their specific tasks. I mean, I'm happy to hear from everyone else as well. I think one of the biggest barriers is the cost and the technical burden, because you really need to maintain this infrastructure, improve it. And also, we also have people really downloading this information quite frequently. And it's, and in some ways you want to kind of educate the community how to use these APIs a little bit more efficiently, so we can provide this information in some way to access. That is where we are kind of thinking in terms of data site commons and expanding. But we're definitely expanding, but really focusing on data site DOIs and the links.
Okay, the one last question before we come. Oh no, there are more questions. Okay.
Okay, this is Henrik Jakob from DBI. Hi, Sarala.
Hi.
Both Sarala and Paolo have mentioned briefly each the usage of data sets. And what do you think, how far are we for data sets from some kind of a realistic idea of what's the impact of a data set is? So for a paper, we can go to any number of well-established sources and get the citation count. Whether you like citation count or not is a different discussion, but it gives you some kind of idea of how much impact a scientific paper has. And if you go to different resources, the number is, let's say, comparable. It always goes in the same direction. So how far or how close are we for data sets from something similar? Is this something, well, it seems it's in both the OpenAir and in the in the dataset effort. It's something you are touching on, so can you comment a bit on that?
So, short answer, because we can talk about this forever. It depends. So, for some communities, very close, because the whole process is rather controlled, quite stable. Data is being produced according to a rationale, published in proper repositories. So we can easily track. This is where, for example, we collect clear, exemplar links between data and publications. Okay, I can mention many use cases of this kind. Then there are other communities, including my own, for example, computer science, which are much less mature. Okay, and those communities don't have repositories of reference where they publish their own stuff. They don't do it according to a practice, even software. We do it through Zenodo, but there's no real practice, right? So, and there it becomes much, much harder. There is the gap between, the maturity gap between some communities and others makes the big difference. And I wonder if in some cases it's achievable in a way, because the variety of data that you have, the variety of validations behind it, the variety of practices that you should have, and the amount of governance that is required to make them stable over time is so high that I'm not sure we'll be able to achieve that peak. In some communities, again, don't want to be. So today, if we look at the graph, there are some communities where you can really observe something real going on, and the numbers are concrete. In others, it's unknown, because there's no way, as your question was really good, to validate that what these people are publishing is a real data set, is not an empty file in a repository with very nice metadata around it, or that the publications from that metadata to a publication are real, they're meaningful. Because I can place a link to another object wherever I want, and that counts as a citation, right? And also for publication, this is becoming somehow in danger in a way, because we can add citations in a way that is easier with respect to the past, to the scholarly communication network, so we should be careful also from that end. But in general, yes, we're not that bad, but we could do much, much better. Short answer. Imagine the long one.
Okay, coffee is
Thank you.
coming, but I have a question, and here's another question in the room. So the interest group of RDA is more about technicalities. Do we need to have an institutional approach to exchange between the graphs? This is my question. So having an overarching institutional approach, getting together all the graphs, not just on technicalities, but on other organizational stuff.
Well, go ahead.
You mean the world government, or?
Kind of.
Say it. Yes. So the thing is that we should have some sort of entity that makes sure that these flows of, let's say, alignment between the different initiatives are kept alive, that they become maybe a de facto standard or something. So yes, RDA is useful today. Maybe in the future it can become something more formal, let's say. And I'd be welcome anybody who likes to do these things, because I'm zero to that.
Okay, very shortly, Raul Palma from PSNC from Poland. So Paolo, I mean, I just want to briefly just to highlight here, maybe that you can also comment a little bit on the potential added value that we can, this kind of research object that you know that we have been working a lot with that kind of connection with the OpenAir research graph and research object, because at the end of the day these are just like mini graphs that we are integrating into this huge research graph, right? And of course we have been also trying to get some value out from that in order to enrich this kind of mini graph that we can create with these. But all of these experiences that had taught us many things. I mean, the challenges, of course, of how to do these kind of crosswalks that you mentioned, of course, as part of the ARDA. Going from, for example, the arrow crate specification, how we can specify all of these entities and put it in the research graph of OpenR. And the other hand, of course, about the quality itself, because like it was mentioned before, so when we were trying to really find some value from all the existing connections, billions of connections that are already available, it was really hard for us to really, find something that we actually found of added value to the things that we already have. So I don't know, it would be maybe good for you just quickly mention how do you see this potential value on
yes,
that.
I think we're also supporters of that, so of these kind of mechanisms, which basically the logic of research objects stays in the fact that we have today connections between objects, publications, data, software, and so on, but we don't have the boundaries of this connection, so how they make sense together as an object. So what you do as a solution, technically, conceptually, is to come up with a new object that points to all those that are somehow connected because they belong to the same experiment. This is done very well by our colleagues of the researchobjects.org initiative. Others are finding different solutions like the RAIDs, the Research Activity Identifier, which resembles quite a lot, but has more of a rigid structure what the research objects are doing. But what would be incredibly useful is to look at these graphs from a research object perspective. That would be, I think it would be one of the next fancy things to do in the future, because you can define manually, of course, a research object, but you can also try to automatically identify the objects that are connected. So to have a sort of research object view of the graph. So when you search and find contexts. You don't find objects, but you find contexts that are aggregating objects according to a logic. And this view would be incredibly interesting to go for, I think. In the manufacturing of these objects, but also in the inference. So you crash an open door, we say in Italy. So I fully agree.
But then some of the links are more trustworthy than the others, depending on the process that's been behind them and the sources. So.
Okay, I think this is the end of the session. Can you blink over to the and give us a warm applause to the audio panel. And then I have a final slide. So if you're interested in this topic, there is a session on Thursday, quite before the noon break, on the semantic interoperability in EOSC. It might be of interest for you. And then there is a session at the EIG workshop in December here in Prague about interlinking interaction between data, publications, and PIDs. So if you're interested, join the sessions. Thank you. Thank you. Welcome.